Hi and welcome to Gaffy's Grinds. This is video 5 in our series on thermochemistry. You're very welcome if this is your first time joining us. If not, welcome back. The usual reminders before we start, guys. Try and eliminate all distractions that might overload your working memory. So we want to get rid of your phone, put it in another room, or at least turn it on to do not disturb so you don't get any notifications. The other thing is make sure you're doing all of the tasks and the questions. If I ask you to speak an answer to a question, it's important that you do it. If I ask you to write questions down, to draw something, it's all part of practicing retrieving information, making sure it's in your long-term memory. If you want to know a bit more about that, go and check out the video on how we learn on my channel. Right, so we're going to talk today about how we've talked already about chemical reactions and the energy changes that happen during a chemical reaction. We're going to talk about today, how do scientists know, how do we measure the energy changes in a chemical reaction? Before we do, we're going to start off with a quick little bit of a revision, I suppose. So I'm going to start off here. This is a thermometer. Now, it's a pretty badly drawn thermometer, but it's a thermometer, right? So this is a thermometer. What does a thermometer do? A thermometer measures temperature. So we're putting this thermometer into a reacting system, which is just a reacting set of chemicals that are doing a chemical reaction. And because there is a change in energy in the reaction, energy is either given out of the system or taken into the system, we're going to get an energy change. If we get an energy change, it's going to result in a temperature change. So say, for example, we have a situation where during a chemical reaction, the temperature of our thermometer goes up like this. Well, what does that mean? Well, the thermometer acts as part of the surroundings. If it's not the actual reacting chemicals, then it's the surroundings. So the thermometer is not the reacting chemicals, it's the surroundings. So we can say if the temperature of the thermometer went up, that means that the temperature of the surroundings increased. So the temperature of the surroundings increased. This is one type of reaction. What is the name given to that type of reaction? You should know that. So by speaking your answer to the screen, I want you to answer that question, please. 1, 2, 3. The name that we give these type of reactions is exothermic. Well done if you got that right. Exothermic reactions increase the temperature of the surroundings because they release energy. So why do they do this? They do this, so this is an exothermic chemical reaction. They do this because energy is taken in to break the bonds. And I'm showing this using an arrow. Well, as you can see, the arrow is quite short. So some energy is taken in to get the reaction to start, to break the bonds in the reactants. And then when the products are formed, energy is given out. And as you can see, the arrow here is much longer. And that's because more energy is given out. So overall, the surroundings heat up because more energy is given out than what's taken in. Straightforward enough, I hope. Right, let's look at the other case. The other case is if we have a chemical reaction and we have our thermometer like this. And in the beginning of the reaction, in the beginning of the reaction, our temperature is like that. And then the reaction proceeds. And by the end of the reaction, our thermometer looks like this. What has happened? Well, the temperature of the thermometer has decreased, okay, which means the temperature of the surroundings has decreased because the thermometer is part of the surroundings. Decreased. Now, one of these two things is always going to happen in a chemical reaction. Either, the temperature is going to go up or the temperature is going to go down. Depends on the energy changes taking place. So what is the name we give to this type of reaction? Quick bit of revision for you. By speaking to the screen, I want you to answer the question. What is the name given to that type of reaction? 1, 2, 3. Okay, you should know that this is an endothermic reaction. Well done if you got that right. Endothermic chemical reaction. Now, why is it endothermic? It's endothermic because, well, energy is taken in to break the bonds. How much energy? Well, it's quite a lot of energy. So I'm drawing quite a long arrow. Now, new bonds are formed when the products are made at the end of the reaction. So energy is also given out. But as you can see, this arrow is much shorter. So overall in the reaction, more energy is taken in than the amount of energy that's given out. Now notice what I'm doing here in this chemical reaction is I'm measuring the temperature. Okay, that's what I'm doing. I'm measuring the temperature using a thermometer. That is not actually telling me how much energy is moving in the reaction. It's only giving me a change in temperature. So if the temperature, so say, imagine we're starting off here at 10 degrees Celsius and we're finishing at 30 degrees Celsius. Well, hopefully you can see that there's been a change in the temperature. How much is that change? Hoping that you can work out that for yourself there. So what is the change in temperature? 1, 2, 3, speak your answer to the screen. The change in temperature is 20 degrees C. It's increased by 20 degrees Celsius. Degrees Celsius is not an amount of energy, that is a temperature. So there is formulas then, mathematical formulas we can use, and we can find using the chemicals we've reacted, how much of the chemicals we have and a change in temperature, we can work out what the change in energy is. Okay, a couple of questions. It's question time for you. Okay, so here is a couple of questions. So what I would like you to do is, in a second, I'm going to ask you to pause the video. When I do that, I want you in your copy or wherever you're going to do these questions to write down the answers using full sentences, the best quality answers you can. Try not to skip anything. Put down something, even if you're not 100%, but you should be. If you've watched all the previous videos, you should be able to do it. So I want you to pause the video and do that now. Okay, so you should only be watching the video if you have tried these questions, and the answers are coming up. Hopefully it's pretty straightforward. The one that you might not, I suppose, I'm just going to speak through them and then I'll put the answers up for you to write down, but listen in first, please. Okay, so is it endo or exothermic? It's exothermic. And how do you know it's exothermic? Because the delta H is negative here. So a negative delta H always means exothermic. You should know that in the previous video. What does a thermometer measure? A thermometer measures temperature. Well done if you got that right. Pretty easy, I hope. It's easy peasy. Describe what would happen to a thermometer during an endothermic reaction. So again, from the previous discussion or the previous explanation, you should know that during an endothermic reaction, the temperature of the thermometer will decrease. Write the molecular formula for propane. So again, you should have we did this in organic chemistry. For propane, it's an alkane. Prop means 3 carbons. So if you weren't already able to do this, so you didn't know what prop meant, try and pause the video and do it now that I've told you 3 carbons. Okay, so you should be watching the video if you have propane done. The formula for propane is C3H8. C3H8. Okay, in the next question, write a word equation for the combustion of propane. So in the previous video, we wrote some combustion equations. Combustion always involves burning something in oxygen. So we are going to react propane and oxygen. They are our reactants. So we're going to write those words on the left-hand side of the arrow. Propane plus oxygen. Arrow, what are the products? Well, in a combustion reaction, again, and we need you guys to know this, you always produce the same products, carbon dioxide and water, when we burn a carbon-based fuel. And of course, propane has carbons. So this is a carbon-based fuel, and it's carbon dioxide and water. So that's your word equation. All right, so I'm going to flip over here now and show you these are the answers. Underneath question 7, you had to do a balanced equation. Again, if you're not sure how to balance equations, you should if you've watched all my videos, but if you're not sure, go and find the video on balancing equations now. So C3H8 is propane, that's the formula, plus 5 oxygens, 5 O2, gives you 3 CO2 and 4 H2O. All right, so guys, it's really important now that you actually correct those, okay? Red pen, correct them if you got them right. If you didn't get them right, it's important that you have a think about why and you fix them, okay? So tick or fix, that's what you're doing at this stage. All right, so we've just discussed combustion reactions. So we're going back over here and we'll see the way we did a small chunk there, then we did some practice, and now we're going back to a new chunk. Okay, so we just talked about propane, which is a fuel, plus oxygen, giving you carbon dioxide plus water. And the balanced equation for this was C3H8 plus 5O2 gives you 3CO2 plus 4H2O. Okay, and that is just the last questions that we did, 6 and 7. So there's nothing new there. Okay, so I'm not going too fast because we've just kind of done that. Now, obviously, when we do this reaction, we're going to get a delta H. Every chemical reaction is going to have a delta H. Delta H, what does this mean, please? So delta H. So by speaking your answer to the screen, tell me what delta H means. So 1, 2, 3. Delta H is a change in energy or change in heat change when a chemical reaction happens. So delta H is equal to, and it's going to be some number, but we're not sure how much. And it's going to be a negative number because this is a combustion reaction. So this is an example of a combustion. So because it's a combustion, and I know that because I'm burning a fuel in oxygen. So because it's a combustion reaction, that means it's going to be a negative number. Now, how much is that number? Well, I'm not sure of that. We would need to measure it to find out. We would never need to measure the heat of the reaction. Now, we're always going to have what we call a unit for this. Our units are going to be kilojoules per mole. So kilojoules mole to the -1, kilojoules per mole. That's what that means. So these are our units. So we're going to have a number and we're going to have kilojoules per mole. Now, how much is it for this particular reaction for propane when we burn it? Well, we don't really know that. Now, you can find these numbers, but how do the scientists discover how much energy it releases when you burn this particular fuel, propane? Well, you do it using a process called calorimetry. Calorimetry is the study of energy changes, basically. Calorimetry, that's what it means. And a word that comes from this is the calorie. Now, you guys probably know that or have heard of that word. Calorie counting is basically where you look to see how much energy is in the food that you eat, because the food that you eat is a fuel, and your bodies, with your own cellular respiration, react it with oxygen in a very similar, it is essentially a combustion reaction. You take a fuel, which is your food, it's a carbon-based molecule, same as propane is. You react it with oxygen and you produce carbon dioxide and water. So your food is storing calories. Okay, so it's stored, and that's why it's called calorimetry. It's the study of the energy in fuels. Now, calorie is the old unit that you used to use to measure energies. We now use the new unit, kilojoule. It's just a more universally, widely used unit, kilojoule now. Okay, so calories are really not used anymore. Even though we still talk about them for food, we don't really talk about them for any other fuels. And if you ever look at the back of a pack of food, you will see the energy values given in calories, or kcal, which is kilocalories, 1,000 calories, and you will see it also given in kilojoules. So both of these are just different units to measure energy. Okay, now how do we get the number then? So using calorimetry, how do we get the number? Well, we would use a device. So I'm going to draw the device now. So I'm going to start by drawing a square. Now, this wouldn't really be square. It's more of a cylinder. It's like a tank. Okay. And inside the tank is another, what we call a chamber. It's a chamber. Okay. And inside the chamber, there's a little heat resistant bowl, a ceramic bowl called a crucible. And into the crucible, you can put your sample, and you will put a known mass of the sample. So you would measure out a specific amount of grams, so a known mass of the sample to be tested. So whatever sample you want to find out, whatever substance you want to find out how much energy it releases when you combust it, you would take a known mass of that sample, probably 50 grams or 100 grams, and put it into the crucible, and then you will put it into this chamber inside this device. what you then have is you have your fuel source, which is shown in red. You then have a tube. Sorry, I want that to be more rectangular. You then have a tube which connects to the outside and it feeds in oxygen. So this is an oxygen supply. Now, of course, oxygen is necessary for combustion, as we see here. So the oxygen needs to be added for combustion to occur. So this tube or feed in allows oxygen to be put into the chamber for burning. Now, we're obviously going to need to start a fire here. So we need to provide a spark of some kind to get the fuel to burn. So we do this electrically. So we have wires, electrical wires. This is a red wire and this is a black wire. And these are electric wires for ignition. These give the spark to get the fuel to start combusting. So electric wires to ignite. You obviously need two, a positive and connected to the positive and negative of a power source, which is going to give a spark and get the fuel to start combusting. The outer tank then, so this chamber inside is sealed. The fuel is able to burn inside there. And then surrounding this is inside the bigger tank is water. So you fill it up with water and you surround the little chamber inside with water. So this is water here. Now, to make sure that the heat is evenly distributed through the water, we've got this device here, which is a stirrer. So it spins around. This is a stirrer. It spins around and makes sure that the heat gets distributed evenly throughout the water. And then obviously we're looking to see if there's an energy change. So how do we measure energy changes? Well, we can use a thermometer. So here is a thermometer. And the thermometer obviously has alcohol, which can rise up, tell us the temperature. Now, this is I should label this as a thermometer. So obviously we're going to burn the fuel inside the chamber, and this chamber is known as a bomb. Like an exploding bomb, it's called a bomb. So inside the bomb, you burn, you put the sample, you seal it, you provide oxygen through the oxygen supply, and then you give a spark, and that ignites the fuel inside the bomb. The fuel burns, and obviously it's combustion, so it's going to release heat, and the heat then is used. The bomb is made of metal, which means it can conduct the heat. And the heat is able to transfer into the surroundings, which is the water, which is like a sleeve of water around the bomb. Over time, as the reaction proceeds, you're going to get a change in the temperature of the water. And by measuring that, then you can work out the energy change. So this whole device is known, because it's got a bomb in it, is called a bomb calorimeter. Okay, now where does that come from? Bomb, because it's got this thing called a bomb inside. Calor, because it measures calories. Meter means to measure. So measure calories. And the bomb is the chamber. So put the fuel in the chamber, burn it, measure the calories. Okay, that's what it does. Now, a bomb calorimeter works by measuring. It can't measure energy directly. It can't give you a number in joules. There's nothing on here. There's no reading where the thermometer does not give joules. There's nothing else, no other device there, a clock or a dial that can tell you amount of joules. So it works by you measure the temperature change. So you measure how much the water changes by, and the water is the surroundings, remember? So however much the water changes by, you measure the temperature change. That's how it works. and then you would use a formula to work out the energy released. You work out the energy released. What scientists often then do then is they adjust the readings, adjust for 1 kilogram of the fuel. Now, the reason why they do this is so that it's very easy for a fair comparison between fuels. Now, if you didn't do this, some scientists might use 100 grams of propane, like above, okay? Whereas another scientist might want to burn some food, like bread, and find out how much it is, and they might just stick a bit of bread in, and that bread might only be 5 grams. And if you don't account for the differences in mass of, 50 grams of propane versus 5 grams of bread, and you just say, okay, that one has 700 joules and that one has 300 joules, that's not really a fair comparison because the quantities of the fuel are different. So they always adjust to 1 kilogram of fuel for a fair comparison. So whatever fuel it is, they might put 50 grams in, and then they would adjust in their calculations. When they're calculating it, they would find, okay, well, that's for 50 grams. How much would it be for a kilogram? So when they adjust to 1 kilogram for fair comparisons, you get a value which is known as the kilogram, because it's 1 kilogram, calorific, because we're measuring the calories, calorific value. So you can be asked this definition, guys. So that's why I'm telling you about it. The kilogram calorific value, what is it? It's the energy released specifically when 1 kilogram of fuel is completely combusted. So it has to be completely combusted. There can't be any of it left behind, which means you need to have a high oxygen supply, because if the oxygen supply runs out, then the combustion would stop. So the kilogram calorific value, guys, is the energy change, the energy released when 1 kilogram of a fuel is completely combusted, that should say, apologies, is completely combusted. All right, so it's probably a good idea, guys, if you make a note of that now. Okay, so make a note, pause the video and make a note of that definition. Energy released when 1 kilogram of fuel is completely combusted. All right, it's practice time. Got a few questions for you guys to practice now. So here they are. There are 4 questions for you here. What I want you to do is I want you to pause the video and try to do these questions for me, please. Okay, so you should only be watching the video if you have paused and given those questions your best go. Okay, again, guys, I'll always remind you, if you don't do these questions, then you're not practicing retrieving, then you're wasting your time doing the videos. Okay, you're just going to forget everything. So if you do the questions and practice, you're going to learn and you're going to retain stuff for a lot longer. That's the whole key. That's what these videos are based on, the whole channel. Okay, so it's really important that you do those questions. Now, well done, guys. If you stick with it, I promise you, you will learn a lot here. Okay, so these are the answers coming up. So foods such as carbohydrates are combustible substances. Name a device that can be used to measure a heat change when these types of substances are burned. Well, foods, fuels, whatever it is, if you want to measure the energy when you burn them, you use a bomb calorimeter. Well done, if you got that right. Next thing is, from memory, draw and label this device. I forgot to remind you, but it's better to try it from memory and get it wrong than to rewind the video back and just copy it, okay? So we never want to copy on this channel. You're trying to do it from memory. So this is what you should have had. These are the parts you should have had and you should have had labeled, and I'm very impressed if you got it all right, okay? So make sure you have the outside calorimeter. So this is the calorimeter. So with the calorimeter, make sure you have the bomb, you have the crucible with the sample and known mass of the sample, you have the oxygen supply, the wires which are for ignition, and then importantly, you have a stirrer to distribute the heat, and you have a thermometer to measure the temperature. And make sure it's filled with water that's labeled. Okay, so all of those are important labels to have in there. Well done if you got that right. If not, pause the video and add any details that you need to. Okay, back to the questions. Small amounts of substances are burned in these devices, but calculations are used to adjust the energy values to 1 kilogram of fuel. Why do scientists do this? Scientists do this so that values of different fuels can be fairly compared. Okay, so fair comparisons between different fuels. That's why scientists do this. They use 1 kilogram of fuel as the reference, so every fuel can be compared evenly. It's not fair to compare 1 kilogram of one fuel with 20 grams of another fuel and just say, well, the energy from that is more than that. Of course it is. You're using a lot more of it. So we use a reference of 1 kilogram. Always adjust to 1 kilogram. When a value is obtained for the energy released when 1 kilogram of fuel is burned, by what name is this known? That would be the kilogram calorific value. Okay, so here are those answers if you need to pause and if you need to record anything. All right, last we'll go back to another little chunk of explanation now. Okay, what about if we want to measure the heat change for a substance, but we cannot burn it? So if we can't burn it in a calorimeter, how do we do it instead? Okay, well, we're going to take a look at a different type of reaction that we didn't really look at in the last video. Different type of reaction, say a reaction between an acid and a base. Both of these are usually liquid substances and they're not flammable. So if they're not flammable, you can't combust them. Now, acids and bases, from our previous chapter, I hope you know what the products are. These are the reactants. These are reactants. Acid plus base. What are the products of a reaction between an acid and a base? So if you know the answer, speak it to the screen now. 1, 2, 3. Acids and a base produce a salt plus water. From junior cycle, you should know that. And if you've studied acids and bases for leaving cert already, you should definitely know that. So these are the products. Now, obviously, if we react an acid and a base to get salt and water, it's a chemical reaction. There's going to be a delta H. There's going to be a change in heat energy. Delta H equals, well, we're not sure yet. Okay, some amount of kilojoules per mole. And this might be positive or negative, we're not sure, but some amount of kilojoules per mole. Now, according to a guy called Arrhenius, okay, and I'll write his name here, Arrhenius was the first person to kind of describe what acids and bases are and try and put a definition on them. So what Arrhenius said that acids and bases always produce certain types of ions. Arrhenius said that acids always are substances which produce H plus ions when we mix them with water. So when we put an acid into water, Arrhenius says an acid produces H plus ions. And Arrhenius says that bases produce OH minus ions when we mix them with water. So that's the definition of an acid and a base, and we kind of still accept it today. It's quite a good definition. It's not perfect because not every acid and base produces these particular ions, but most of them do. So we can still use them quite well today. Now, when two substances produce these particular ions, I hope you can see that these two things could join together, H plus and an OH minus, could mix together to give you this. That's where the water comes from in a neutralization reaction. Because the acid produces H plus and the base produces OH minus, one of the products is always water because these two things are always produced. Okay. What about the salt? Where does that come from? Well, that depends on what else is joined with the H plus and the OH minus. So something is going to be joined with the acid. It's going to be X minus basically plus H plus. This is an ionic substance, X minus and H plus. And something else is going to be joined with the base. It's usually going to be a metal, a positive cation. So we'll call it Y plus. So that could be any cation, any metal, any cation. So obviously, if the H plus and the OH minus react to give water, well then that must mean that the X minus and the Y plus are going to react together to give the salt. So that's how you can always work out the salt is going to be. Take away the OH and the H and the OH to make the water, and whatever else is left, that's going to make your salt. Now, this particular type of reaction, whenever we get a substance that produces a H plus and an OH minus, an acid and a base, and they react together, we call this particular type of reaction, we call it a neutralization reaction. So this is a neutralization reaction. Okay, so a neutralization reaction. And that means that this heat here, this delta H, is known as the heat of neutralization. So if we're talking about a neutralization reaction, then the heat change can be known as a heat of neutralization. So how would we actually define in proper, in a perfect definition for the heat of neutralization, or for a neutralization reaction, or heat of neutralization? Well, it's obviously a heat change. This guy down here is the heat change when, now think about what's happening. Well, we're reacting H plus and OH minus. How much of it are we reacting? We're going to go at 1 mole. So we're going to always have to make sure that this is a 1 and a 1 ratio. Okay, so it's the heat change when 1 mole of H plus ions from an acid reacts with 1 mole of OH minus ions from a base. Why is it 1 mole and 1 mole? Well, they react in a 1:1 ratio to give us H2O. So H and OH, 1:1 ratio gives you H2O. So this is what we would call the heat of neutralization. So there is another new definition for us. Heat of neutralization is the heat change when 1 mole of H plus ions from an acid reacts with 1 mole of OH minus ions from a base. Now, how would we go about measuring heat of neutralization? We can't put it in a bottom calorimeter. Well, there is an experiment, and I am going to do it in a future video coming up soon. I'm going to do a much more detailed video on this experiment. But as a short as to how we would measure the heat of reaction for something that we can't burn, combust, we would take an insulated cup, so something like polystyrene. We would use polystyrene because it is a better insulator than something like glass or ceramic or even paper. It's a better insulator, which means that we can more accurately measure heat changes. If heat escapes during the reaction, then we're not measuring it. So we use a polystyrene cup. Into the polystyrene cup, we will put our reacting mixture. So in this case, if we're talking about a neutralization reaction, we would put acid. We would have to know the amount. So say we took 50 mils of acid and we put in plus 50 mils of base. So we're going to start a reaction. Right, good. How are we going to measure the energy change? Well, we can't directly measure the energy change. We can't directly measure the joules. But just like before, if we can measure the temperature change, then we could work it out. So to measure the temperature change, we're going to use our trusty thermometer. So we're going to put our thermometer into the cup, which acts as the surroundings, remember. So if there's a heat change, energy is going to flow either into the thermometer or away from the thermometer. And we're going to put our thermometer in. It's got an alcohol, and we also would usually put a cap on. And what the cap does is, again, it traps heat. It stops the heat from escaping, and it allows us to more accurately measure the temperature change. So this is a thermometer and a cap. Now, let's look at a couple of things that might happen here. So it might happen that we start and we've got our thermometer, and our thermometer has a reading of 10 degrees. Ooh. Say our thermometer starts at 10 degrees Celsius. And as the reaction proceeds, the thermometer changes to look like this. What has happened to the temperature? On 3, what would you say has happened? 1, 2, 3. The temperature has increased. So say it's gone up to 30 degrees Celsius. Now, what does that mean about the energy of the surroundings? We would say the energy of the surroundings what has happened to it? It has increased. The energy of the surroundings has increased. What type of reaction is this? On 3, 1, 2, 3. This is an exothermic reaction. Now, if you said endothermic, that would be wrong. Okay, this is exothermic because the system has released energy to the surroundings, and the surroundings has gone up in temperature. Remember, the thermometer is the surroundings. Now, if I wanted to work out what the change in temperature is, I would write this as delta T because it's temperature. Now, note the difference. This is not delta H. That would be change in heat. This is delta T, change in temperature. What would it be for this reaction? How would I work it out? So on 3, I want you to speak to the screen. How would I work out the change in temperature? 1, 2, 3. Okay, so I would do it by doing 30 minus 10. And that would give me a change in temperature, which is equal to 20 degrees. What about a second scenario where I put my thermometer in at the start and just like before, the temperature is 10 degrees. But as the reaction proceeds, the temperature goes down. So it's less now. So it's now only, say, 6 degrees. Well, what's happened to the energy from the surroundings? Energy of surroundings has decreased as temperature has gone down. What type of reaction is this? On 3, 1, 2, 3. This is an endothermic reaction. So energy of the surroundings has decreased. This is endothermic. Okay, what would the delta T be? Delta T equals, figure that out for me, please. Pause the video and figure that out. You can probably do that in your head. 1, 2, 3, pause the video. Okay, this is what you should have. 10 minus 6 equals 4 degrees Celsius. Well done if you got that. Now, one important note is that delta T does not equal delta H. They are not the same thing. So you cannot just say, oh, the change in temperature, the delta H for that is 4 degrees Celsius. That would be wrong because that is a change in temperature. But you can use the change in temperature using some formulas, which I will talk about when I do the video on this particular experiment. I will talk about that formula. You can use the heat change to work out what the delta H is. Okay, so it's not, delta T is not equal to delta H, but it can be used to find delta H. Okay, time to do some practice. So you should be able to do all of those. So I want you to pause the video and I want you to try to do them questions now, please. Okay, so you're only watching the video if you have managed to have a go at them questions and you've given them your best shot. According to Arrhenius, acids always produce, that should say H plus ions. Well done if you got that right. Now that I've told you that one, if you didn't get the second one, go and do it now, please. Pause the video and do it. Okay, you should be watching the video now again if you have got the second part done. So according to Arrhenius, bases always produce OH minus ions. So acids H plus ions, bases OH minus ions. When an acid and base react, they usually produce the same type of products. What are the products? So what are the products in an acid-base reaction? They are a salt, and water. Okay, so a salt and water. Write a word equation for the reaction between hydrochloric acid and sodium hydroxide. Okay, so what you should have here, I'm just going to flick over here. is this one here. Hydrochloric acid plus sodium hydroxide. They are your acid and your base. They are your reactants. Your products then, obviously there's your water. And what is the salt? Well, it's the other part. So here's our hydroxide forms with our hydro. Okay, so you've got hydrochloric acid, that's your hydrogen, and hydroxide is OH. Well, what else is there then? We've got a different color. We've got chloric, so chlorine, and sodium. So they join together to give us sodium chloride. That's our salt. Okay, this is a salt. So salt plus water. And then underneath that, we would write our, the next question asks you to do a balanced equation. So for the word equation, do a balanced equation. So hydrochloric acid is HCl. Sodium hydroxide is NaOH. Sodium chloride is NaCl. And water is H2O. Again, if you've done all my videos, we've talked before about how to write the formulas for compounds. So you should be able to do all that. Okay, that is already balanced. We don't need to mess around with it. All the atoms are accounted for. Number 5 says, in the reaction between acid and a base is carried out in a polystyrene cup. What is the purpose of the lid? The purpose of the lid is to stop heat escaping so the temperature can be measured more accurately. Well done if you said that. Stop heat escaping so you can measure the temperature accurately. Why is polystyrene used instead of a glass beaker? Polystyrene is a better insulator and it stops heat escaping. Again, it allows us to measure the temperature accurately. When doing this experiment, how would a student know if it was an exothermic reaction? So without looking back, exothermic releases energy to the surroundings. Part of the surroundings is the thermometer. So what would happen if energy was released into the thermometer? The temperature would increase. So the student would know it's exothermic if the temperature on the thermometer increased. And lastly, Jenny measured the temperature change for this reaction and found out that it went from 10 degrees at the beginning of the reaction and reached 18 degrees at its highest. Jenny says that the heat of neutralization for the reaction is 8 degrees Celsius. Explain why she is wrong. Okay, well, maybe this was the most challenging one. Okay, so why is it wrong? Well, it's wrong because, first of all, this is the bit we're focused on. She said that heat of neutralization, heat, was 8 degrees Celsius. Degrees Celsius is not a measurement of heat. Heat is measured in joules. Degrees Celsius is a measure for temperature. So this is wrong because Jenny is talking about temperature. So let's see what I've written. She is wrong because 8 degrees is the change in temperature. It is not a heat or energy. It can be used though to calculate the heat of neutralization. So that's what I have written. You compare it to your answer and see if you need to add any little bit. So I would say what I've written there is a good answer. Okay, so compare it to your own and see if you're happy with your own still. All right, that's the end of that video. I'll see you in the next one, and I look forward to seeing you. If you found this video useful, if you could give it a like, it helps other people to find the video who might need some help with chemistry as well. And it also, if you have any other videos you would like me to discuss or any other topics you'd like me to discuss, stick a comment down below and I can get planning on making one as soon as possible. Okay, so I look forward to seeing you in the future videos.